on, so that should be fine.
Whichever you want.
Yeah. Right, I'll get started because I think just a couple of slides to go through here. So it's a bit of a controversial topic because whenever you talk about something that has already been established for 40 years or 50 years, and this is the current standard of practice, so it becomes a controversial topic. So it's mainly going to talk about the limitations of the current design practice for steel strip walls, but some of the comments that I'm making is also applicable for geogrid walls, so if somebody is interested. Mainly I'm going to focus on two design methods, AASHTO Simplified and Coherent gravity. So those are most of my comments are related to those two methods, those two methods are the current state of practice if you look at these guidelines. But other methods, some of the comments are also applicable for other methods listed here because they all have somewhat similar framework. So no need to read about this one, but just wanted to highlight that the paper that I've written, I'm discussing several limitations, but I don't have the time to go through each and every issue, but I'll be focusing on select topics listed in this one. So just before we get into the details, I just wanted to highlight how we develop these existing design methods. And you might have already seen these equations. For example, now looking at this one, this is how we calculate the reinforcement load. Looks analytical, but it's a totally empirical solution. So you have a vertical effective stress, and then you have the area, which is the tributary area that you are concerned with if you are designing a particular reinforcement. And then you have a K factor. K is the lateral earth pressure, which is, in fact, it's not an earth pressure to be precise, but it was derived mainly from instrumented walls. That's something that we sometimes overlook. And so what we do is we have walls like this, and then you have instrumented walls, and then the reinforcement load distribution. So if I have 3 layers that are instrumented, then you have 3 data points. And from there, you not only one wall, you look at several other walls, and then you develop like an envelope. And from there, you calculate the K. So that's how these design methods are developed. So one thing to highlight is that these are all working stress-based methods, and they are well developed using walls that are under working stress conditions, and they are also validated under working stress conditions. So, but we know the factor of safety is not only working stress conditions, but also the ultimate conditions divided by the working stress conditions, right? So the problem is that we haven't tested these design methods under ultimate conditions, and I think that's where most of the problems are. It's especially with respect to steel strip walls. So I'll give you one example, and this is a very special wall because considering that all the walls that we have, this is the only steel strip wall that's out there in public domain that's been loaded to failure. So this is the only wall that you can test your theory for the ultimate condition, right? So this was done way back in 1976. So even right now, no matter which method you use, you will say that this wall should fail under pullout in the upper reinforcements. That's how it's going to fail. And so 3.6 meter high wall, purposely under-designed, by the way. So they construct the wall, nothing happened, 3.6 meter high. So it deflected by only about 5 millimeters. So it's not a wall that's going to fail under pullout. So people who did the test, they waited for a couple of days, nothing happened, and they started loading again. So they went on loading, and they went up to 90 kPa. Then that's when the wall failed. It's not because of the pull-out of the upper reinforcement, but it was a connection failure at the bottom reinforcement. So it's totally different failure mechanism. So to this date, I think we cannot explain what happened in this wall, why it didn't fail in the first place, and why it failed in a totally different way after surcharge. So I think it's a lot to do with the way we calculate the ultimate condition. So, for example, we have 3 failure modes when it comes to MSE walls. You have the tensile rupture here, and it could fail at the connection, and also you have the pull-out failure. And what we do is, we calculate factor of safety for each and every reinforcement layer for those 3 failure modes. And we assume that if you have a factor of safety less than 1 for one of those failure modes, then your whole thing is going to collapse. That's a big assumption. I think that's where we need to look into the details a little bit more. It might be a fair assumption for these 2 failure modes, like for steel strips especially. But what about pull-out? I mean, some of you have done MSE wall design, and you might find it sometimes it's difficult to get the factor of safety that you need at the top reinforcement for pull-out. So, but how it's going to fail? Because if it needs to fail, then you have to intersect other reinforcement layers as well. So it cannot fail it by itself. So if it want to fail it by itself, then you have a different failure mechanism, and then you have a longer reinforcement length. And then that's why we don't see a lot of pull-out failures in practice. As far as I know only one failure that happened like that. So how do we look at this problem in a different way? And I just want to introduce this quick method. It's a totally analytical method, by the way. It's all other methods that we discussed here, they're empirical. This is analytical, and it's based on the simple concept. I'm not going to details here, but in principle, what you do is you're trying to get the resistance side and the demand side. The demand side, we know that is earth pressure, compaction load, or surcharge, or whatever, or even seismic. So when it comes to earth pressures, we know that if you have 0 displacement, you have at-rest conditions, right? And then with some deflection, you reach active conditions. So that's the demand side. So what about the resistance side? So if you have 0 deflection of the wall, then geogrids or reinforcements, they're not going to contribute. So let's say now the wall deflects a little bit. So what I'm going to do is I'm going to take the moments about this point, and then I can calculate how much of resistance that these reinforcements are making. So here, let's say I'm at this point. Still, it's not enough to reach the equilibrium. So the wall should deform more. So eventually it'll reach at-rest conditions. So now the wall is in equilibrium. So I can even push this one even further and see what the ultimate capacity of this wall is. Well, it's not, I don't want to get into the detail there. But the question is, how do you calculate this reinforcement load? So that leads to my only slide with the equations here, but I don't want to get into the details, but it's just want to tell you that you can solve this problem analytically. You look at the element and you write some equations down, and these are not very complex equations, sine and cosines, and these kappa lambda factors, they are not empirical. They are functions of friction angle, reinforcement stiffness, Poisson's ratio, and those things that we all know. So those are the basic equations, and if somebody is interested, I can even send you a spreadsheet where you can have those equations down, and you can solve the wall for you. So let's go back to the wall that we discussed. So if we look at the wall at the working stress condition, before we did the surcharge, and now you see that wall is actually, you can reach equilibrium. And in fact, the factor of safety that I calculated is something like 1.8. So that's why it didn't fail. And then if we surcharge it to 90 kPa, now you see that it reaches the point where almost close to equilibrium, and it drops afterward. And the drop is because of you reached the capacity of the reinforcement at the bottom layers, and that's why it drops after that. And I made it come down because once it reached the ultimate conditions, that's why it's coming down. So now you can explain what happened in that wall, but totally in an analytical way. And one of the other bigger problems is that with the existing methods, as you know, there's no way you can calculate the connection load, facing the load at the facing, for example, here. So that's one of the challenges in explaining this method, because we know that it failed at the connection. So if you don't know how to calculate the connection load, so how do we explain that? Because right now what we do is we assume that we have the peak load, and we think that the connection load is same as the peak load, which is unlikely, because the only way you can have that is if you have frictionless material there. Otherwise, you should drop down. And here with the calculations that I did, this is the connection load, basically these numbers here. So at a certain point, when we reach 90 kPa, it reaches its limits. That's why it failed. So there's some interesting thing about this issue. Let's say, going back to that wall again at the working stress conditions, I said it's not going to fail. But look at the reinforcement load distributions. So the upper 4 reinforcement, you mobilize the full resistance of those reinforcements. And basically saying the factor of safety is 1. And there's no reserve capacity in these 4 reinforcements. So you might think, okay, this is a wall that this is under-designed, purposely under-designed. So that's why it's happening. But let's look at this wall. This is a wall from Illinois called Minnow Creek Wall, and designed for AASHTO, based on AASHTO. And very stable wall, by the way. It's a 17-meter high wall, and once it's constructed, it deflected only by 40 millimeters. So it means that it's a very stable one. And I calculated this one using the method that I just explained, and I think that even with 150 kPa, it won't even yield some of these reinforcements. So it's very stable. But look at the reinforcements at the top, maybe 5-6 meters. So you see the full reinforcement length is mobilized in those. So basically, the factor of safety is 1, but we know that in AASHTO, when we do the calculation, the pull-out minimum factor of safety should be 1.5. So where's the minimum factor of safety of 1.5 here? So there's a discrepancy between what we do in the calculations versus what we see in the practice. It's common in most of the steel strip walls, and you can explain why this is happening. I'm not saying that we need to extend the reinforcement length, but that factor of safety is built in already. And one of the issues is because of the way I think a lot of problems are due to the tributary area method calculation. So usually we don't see issues because what we are dealing with is uniformly distributed walls where you have reinforcement. Like, let's say this type of wall, you have 3 layers of reinforcement. So if I were to calculate the force on the this particular reinforcement, I know this, you have to calculate the area of that trapezoidal, so that will give you the load. But let's take a hypothetical case where you have all 3 reinforcements at the same level. So now, what's the distribution? So now you have totally different distributions for the 3 layers. Although they're at the same level, they'll feel the same vertical stress. They have to deflect the same amount, but they're having totally different loads there. So this is a hypothetical case, but you can do even numerical modeling and see what's happening. But the difference between the tributary area methods and the method that I just explained is that now with the SRI method, you'll predict the same reinforcement load for all 3 layers. So it's not only like the like there's some practical implications as well for that issue. For example, some of you have dealt with these horizontal and vertical obstructions. So FHWA says that, okay, you can put some additional reinforcement to compensate for shorter geogrids or reinforcements. So, but I find that people tend to be a little bit hesitant to do that because as you put additional reinforcement there, your tributary area goes down and you don't see the same effect from those reinforcements. So there are some issues with the current way of analyzing those problems. And there's another problem with the walls that I've analyzed so far. What I'm seeing is that it's demonstrated even in the previous wall that I discussed, is that you need sometimes you can make a wall more robust by having longer reinforcement at the top because that pull-out is governing that. And the bottom reinforcement, you probably don't need longer reinforcement, but the strength is controlling that. So it might make more sense to have either thicker reinforcements or maybe more like closely spaced reinforcements. But this type of truncated base walls, it's not encouraged in the design practice. One of the reasons being that the database that was used for the development of these design methods was based on uniform reinforcement lengths. So you cannot extend that to truncated base because we don't know what's going to happen. So that's one of the limitations. But it's a bigger problem if you have a competent soil or bedrock. Do we want to excavate that whole thing out and put uniform reinforcement length just for the sake of satisfying the database requirement, right? So so those issues, and this is another interesting one. Let's say you have a wall, let's say it's deformed, rotating about its base. So natural inclination is that we think that, okay, you have to have active conditions at the top, and then you will probably have near at-rest conditions at the bottom. So this is what people like Chan, they did some work, and I think that's what our understanding. But MSE wall behave the other way around. So you have at-rest conditions at the top and the active conditions at the bottom. And the people have said, okay, well, that's because of the compaction forces, compaction stresses. That could be right, but why don't we see the same effect in the geogrid reinforced walls? And then also some say, okay, you cannot use the tributary area, like the traditional earth pressures for MSE walls. But in fact, what we can see is that it's nothing to do with the earth pressure theories, but it is wrongly interpreted as an earth pressure, because what happens is the reinforcements the upper reinforcement needs to stretch. So they see larger forces, and that's been interpreted as a higher lateral earth pressure. That's basically what's happening. So it's nothing to do, there's no contradiction with the earth pressure theories. So just last two slides. So it's in general. So with this method, I don't want to get into details, but with this method, you can explain some of these observations. Like this is a simple one. We know that steel strip walls deflect less than the geogrid walls. So those things can be explained using these diagrams. This is a demand versus resistance curve that I just explained. And also these normalized force distributions. For example, as for steel strip walls, it generally tends to be triangular. Geogrids, it's trapezoidal, and that's field observations. And analytical also, you can explain why it's happening. It's there. Why you get these shapes. The difference is that this is the input to the equation in current design methods. But in this one, this is the output of the method. So, and don't want to get into details. Some of you might remember this F star factor. So it's an empirical coefficient right now, but even that you can explain why it's like that. It's just the dilation effect. And then also some other interesting questions. There are papers about okay, why facing is important for certain types of wall and not for others. So you can explain by looking at these distributions, for example. So last slide, and there are several advantages of this analytical method, but I just want to highlight two things. So I think we need to look at how we calculate the overall factor of safety in a different way, accounting for, especially looking at realistic failure modes. I think that's one aspect. And there's another aspect which I didn't get a chance to talk here, but it's actually when you analyze the geogrid versus steel strips or whatever, there's no fundamental difference between those two walls. It's just, if you have the framework correct, all you need to do is put the right reinforcement stiffness and you'll get the behavior. So it's you don't need to switch from coherent gravity to tieback or different methods depending on the wall type. So that's pretty much it.
We have a few minutes for questions if anyone has any. Well, Linda, thank you very much.
Thanks.
Pleasure. Thank you. All right, our final